Today we will start with AC circuit. In DC current circuits, Ohm's law and Kirchhoff's laws are sufficient, and the only resistances met with are ohmic values. But in AC circuits, the currents and EMFs are changing in value and phase, and we have to make use of inductance and condenses besides ohmic resistances. So we have seen many DC circuits and in which ohmic resistance are considered, and so Kirchhoff's laws are sufficient to explain the circuits. But these laws are sufficient to AC circuits also, but since the currents and EMFs are continuously varying in phase, we have to consider inductances or inductive reactance in case of AC circuits. The applied alternating voltage of a pure sine wave form will be represented by E is equal to E0 sine omega t, and the current through component under consideration will be represented by I is equal to I0 sine omega t, where E and I indicate the instantaneous and E0 and I0 the maximum or peak values of applied and currents respectively. So since the currents and EMFs are changing in the AC current circuits, the value of EMF is represented by the equation E is equal to E0 sine omega t, and the current is represented by E is equal to I0 sine omega t, where E and I are the instantaneous EMF and I in the instantaneous EMF and current in the circuit, and E0 and I0 are the maxima or peak values of EMF and currents in the circuit respectively. And omega is equal to 2 pi f, where f is the frequency of alternating potential or current, and f is representing the frequency of alternating current. The term omega t or 2 pi f t is called the phase angle, and any difference between two values of this term is called a phase difference. So omega is 2 pi f, or omega t is equal to 2 pi f t is known as the phase angle. So any difference between two values of this term, 2 omega t means different omega t values, so is called the phase difference. So difference between these omega t values represents the phase difference, since omega t is the phase angle. Physically, the phase difference is an interval of time and not an angle. The relation theta is equal to omega t serves to connect the terms and the angle factors. Since omega t is equal to theta, this is actually a interval of time sorry the interval of time and not an angle. Now the method of solving AC problems or AC circuits problem are, there are three methods. First one is by writing down the equations of EMFs and currents in the circuit and finding out their solutions. The second method is by drawing vector or phase diagrams and solving by geometrical methods. And third method is using the J operators. The first method is you have already seen in the DC circuits. What we are doing is we will find out the EMFs and instantaneous values of EMFs and currents in the circuits so that we can solve the AC problem. This is first method, and another method is vector or phase diagram. You will draw the variation of potential and current in the same graph that will represent the phase diagram, or we will draw a graph between this current and potential so that we can find out the variation between these two values. That is this method. And the method of J operators, which you have already seen, we have already discussed in our previous class. Okay. Now we will consider many circuits, that is circuits containing different components: resistance, capacitance, inductance, and the combination of these components. So first we will discuss about AC through ohmic resistance. Let an alternating voltage E is equal to E0 sin omega t be applied to a circuit of non-inductive resistance R. Non-inductive resistance means it's a purely ohmic resistance. So we have shown here a circuit which is a resistance, and AC is applied to this circuit, and its potential is given by E is equal to E0 sin omega t. I is the current in R at any instant t, where E is the instantaneous and E0 is the maximum value, just as we explained, and which is also called amplitude of the applied alternating voltage. The potential difference across the resistance R being equal to the applied voltage at that instant, we can have the method of solving this is just as the problems we discussed in the DC circuits. What we are doing is we will consider the total EMF in the circuit, applied EMF, and what is flowing across these components, and we will equate these two and solving the equation. This is the method. So we can write the applied EMF, we can write as E, which is nothing but I into R, because this applied voltage is dropped across this ohmic resistance, so it can be represented as I into R, but E is equal to E0 sin omega, which is the applied EMF. So we can write I is equal to E by R, which is equal to E0 sin omega t by R. E0 by R is represented by I0, can be represented as I0, so that it will become I is equal to I0 sin omega t, where I0, which is E0 by R, is the amplitude of the current. Thus the current and voltage rise and fall simultaneously, or they are in phase with each other. So what we have seen from this equation is that we have got the instantaneous value of current in the circuit as I is equal to I0 sin omega t, and applied EMF is E is equal to E0 sin omega t. So the phase angle is same here, omega t and omega t. So since it is a sinusoidal function, the EMF is sinusoidally varying and I is also varying. So the current and voltages are simultaneously varying in phase with each other. In phase means there is no phase angle between these two values. So these are sinusoidally varying in phase. This is represented in this graph. So this upper curve represents the value of E. Since E is equal to E0 sin omega t, I is equal to E0 by R sin omega t, which means this E0 value is reduced by a factor of R, since R is appearing in the denominator. So this amplitude is less than this E0, since here it is E0 by R. So the peak will not reach up to this, but they are in phase. That's why this graph appear like this. So the peak of this, or the amplitude of this I, will be less than this amplitude of this potential. So that's how this graph appears. So this is about AC through pure ohmic resistance. Okay. Next we will consider AC through an inductance only. An inductance circuit. So we will consider a circuit in which AC is applied through an inductor coil. Okay. So when an alternating EMF is applied to send an AC through an inductance of negligible resistance, since it is varying in strength and direction, a back EMF at every instant is produced due to self-inductance, which opposes the rise and fall of current. And in order that a current may just flow through it, the applied EMF must be at least equal to and greater than the back EMF. So you know the theory of inductance coil. So what will happen? An alternating current when flowing through such coil will produce a self-inductance which may produce an EMF which will be opposing the applied EMF. So in order to flow the applied EMF through the circuit, which have to be a little greater than the back EMF produced in the coil. So the EMF of the circuit can be represented as, let E is equal to E0 sin omega t be the applied voltage as usual, and L is the inductance value, and E is the back EMF at any instant, which can be represented as L into di by dt. This is the back EMF. So the total EMF in the circuit can be represented as E minus L into di by dt is equal to 0, because the applied EMF have to be much greater than this back EMF in order to overcome this back EMF to flow through this circuit. So E is equal to minus L into di by dt is equal to 0. This can be represented as E0 is equal to sin omega t is equal to L into di by dt, from which di by dt can be represented as E0 by L sin omega t. So if we are integrating both sides, we will get I is equal to E0 by L omega into cos omega t, plus integrating sin omega will give you cos omega t by omega. That factor is appearing here, a minus sign also while integrating, and this is a constant of integration. So the constant of integration has the dimension of current, since it's the current equation, and is independent of time. Since source has an EMF which oscillates symmetrically about 0, the current it sustains also oscillates symmetrically about 0. So there is no time dependent component that exists. This constant is equal to 0. So we can write the constant of integration as 0. So that I can be written as minus E0 by L omega into cos omega t. This can be represented, since there is a minus sign and this is cos factor, so we can represent it as a sin omega t minus pi by 2. So we will get I0 sin omega t minus pi by 2. Thus the current in the inductance lags behind the applied EMF by pi by 2, or the applied EMF is ahead of current by pi by 2. What does this equations mean? I is equal to I0 sin omega t minus pi by 2. But our potential equation is, or applied EMF equation is, E0 sin omega t. So this is omega t and this is omega t minus pi by 2. That means the current through the inductance coil is lags behind the potential by a factor of pi by 2, by a phase of pi by 2, or we can say EMF leads the current by pi by 2. Okay. The back EMF, however, lags behind the current by pi by 2 or 90 degree. So we can represent this as in figure. This is voltage and this is current. So this will have a phase difference of 90 degree. This voltage is leading the current. Back EMF can be represented as L into di by dt minus L into di by dt, that is minus E0 sine omega t or 1/4 of a cycle, and it lags behind the applied EMF by pi. So back EMF is applied behind the lags by pi degree. Total of. For if I is equal to I0 sine omega t be the current, self-induced EMF is given by, this is our equation, E is equal to minus L into di by dt minus L I0 omega cos omega t, which can be represented in sine form as this. So we can represent this as yes, this is a phasor diagram. Phasor diagram of this E and I. This is omega t and this is the fluctuation. So this represents the omega, E, and this represents the current, which lags by an angle of pi by 2, because the peaks will appear in a pi by 2 difference, 90 degree difference. Okay, so this you have already seen in your higher secondary classes. So I0 is equal to E0 L omega is the amplitude of the current. The quantity L omega analogous to the resistance and is called the inductive reactance. So L omega is called the inductive reactance, which is similar to the resistance in the purely resistance circuit. So XL is equal to L omega. We represent this inductive reactance by the term X with suffix L, which is L omega, which is the resistance offered to the flow of AC through the inductance. So which is known as inductive reactance. So XL can be represented as L into omega, which is omega is 2 pi F, so 2 pi F into L. So where F is the frequency of the AC. So I0 can be represented as E0 by XL, which is the usual definition. I is equal to V by R. So here it is E0 and this is 2 pi F by L. So that E0 can be written as I0 XL, which is I0 2 pi F into L volts. So this is the peak value of current and peak value of voltage. The XL can also be represented as RMS value of alternating EMF across inductance by RMS value of corresponding current through the circuit. T by XL is known as, I by XL is called susceptance. Susceptance of the circuit. So these are all about the AC through purely inductive circuit, or a circuit having inductance only. So we have seen the circuit having resistance and inductance separately. Now we'll see or we'll discuss about a circuit containing resistance and inductance in series. That this combination of this resistance and inductance in which an AC is applied. So here L represents the inductance and R represents the ohmic resistance. When an alternating EMF is applied, an AC will flow through the circuit. AC will flow through the circuit. I is equal to I0 sine omega t be the AC at any instant. Due to changing current, an induced EMF is set up in the inductance, which opposes the applied EMF, just as we discussed before. And this can be represented as E is equal to minus d phi by dt, which is nothing but minus L into di by dt, where phi is the flux, which can be represented as L into I, where L is the self-inductance. So the applied EMF is equal to which is equal in the circuit is equal to E minus L into di by dt. By Ohm's law, we can represent I as E minus L into di by dt by R, assuming that the inductance has no ohmic resistance, only inductive reactance. So by Ohm's law, the current in the equation can be represented like this. But di by dt can be represented as omega I0 cos omega t, which will be obtained from the equation I is equal to I0 sin omega t. So integrating this will give you, differentiating this will give you di by dt, which is this. So E minus L into I0 cos omega t will give you I into R. This is the EMF equation of this circuit, this combination circuit, LR series combination circuit, where I is I0 sin omega t. So this I0 R sin omega t. Now taking this term into the right side, we will get E is equal to I0 R sin omega t plus omega L I0 cos omega t. Here what we are doing is we are taking this I0 as a common factor. I0 is common factor which is taken outside the bracket. So we will get one more, you can write one more step, I0 into R sin omega t plus omega L into cos omega t. Now what we are doing is we are multiplying this equation, multiplying and dividing this equation by the factor square root of R square plus omega square L square. And the multiplying factor is keeping outside the bracket, and the dividing factor is distributed among these components. So we can write this equation as I0 into square root of R square plus omega square L square into R by square root of R square plus omega square. So the total effect is nothing. So this equation is same as this, but we have but we could write it is in a new form by this factor. Now we are putting cos phi is equal to R by square root of R square plus omega square L square. That is this term. This term is cos phi and this term is sin phi. Okay. From these two we will get tan phi as omega L by R. So this equation become E0 into square root of R square plus omega square L square into this factor is cos phi, so sin omega t cos phi plus, and this factor is sin phi cos omega t into sin phi. So this is sin A cos B plus cos A sin B form, which is nothing but sin A plus B. So this equation is reduced to I0 into square root of R square plus omega square L square into sin omega t plus phi. When omega t plus phi is equal to pi by 2, when this factor is equal to pi by 2, this term will converge to 1. So that we will get I is equal to I0 into square root of R square plus omega square L square, which is nothing but E0. This is the maximum value of potential. So we can write E is equal to, so this term is now E0. So we can write E is equal to E0 sin omega t plus phi, where I is I0 sin omega t. So this implies that the EMF E leads the current by phi, or I lags behind E by phi. So we have got these equations, two equations. E is equal to I0 sin omega t plus phi finally. And we know the current applied in the circuit is I is equal to I0 sin omega t. So if you are looking these two equations, comparing these two equations, we can find that EMF leads the current by a phase of phi. This implies that the EMF leads the current by phi, or I lags behind E by phi, where phi is tan inverse omega L by R, where cos phi is equal to R by square root of R square plus omega square L square is called the power factor of the circuit, which can have any value between 0 or phi is equal to 90 degree and unity for phi is equal to 0 degree. So Cos phi is known as the power factor of the circuit, where phi is given by this equation, and according to the value of phi, whether it is 90 or 0 degree, this power factor can vary from 0 to 1. The quantity square root of r square plus omega square L square plays the same part in AC circuit as in ohmic resistance R in DC circuits. R has the limiting value for very low frequencies, and omega square L square, which is the reactance for high frequency.